started. So today we're delighted to have Semyon Alesker here, who will speak about theory of valuations and manifolds.
The goal of this talk is to give a brief introduction to the theory of valuations on manifolds. Roughly, valuation of manifold is a finitely additive measure, the class of all differentiable polyhedra is a manifold of some very special form. The space of valuations has a number of non-trivial structures, and I think space of valuations, in particular multiplicative structure, and I think space of valuations equips any smooth manifold with new kind of structure. This notion of valuation of manifold was motivated by the classical notion of valuation on convex sets, which has been my main interest for many years, but my talk is completely independent of this story. And to generalize some parts of this classical theory beyond complexity to manifolds. Let me mention a few names of people who contributed to this theory, and now I will mention some applications of this theory, the name of people. So, main applications of this theory, I will not discuss today applications in any details, I just mentioned a few names, applications to integral geometry. This is due to Bernick, Fu, Feifman, Wannerer, myself. Also, there are rich and relatively recently discovered connections to pseudo-Riemannian geometry. This is due to, again, these are the same people with various combinations. Bernick, Feifman, Solanas, and Keller geometry, most recently. Bernick, Fu, Solanas, Wannerer. Okay. My next goal is to introduce the notion of smooth valuation of the manifold. So let us fix a smooth manifold M, dimension n, and let me define the notion of differentiable polyhedron. So definition, differentiable polyhedron P in the manifold is a compact subset that locally diffeomorphic to R P times non-negative numbers R cubed. So, for example, closed submanifold is a differentiable polyhedron, or even if it has boundary, it's also a special case of differentiable polyhedron. They may have any dimension between 0, like point, and dimension of the whole manifold. Now I'm going to give a few technical definitions before I introduce the notion of valuation. Okay, so next definition is tangent cone. So if we have differentiable polyhedron P and a point inside it, then we define tangent cone to be a subset of tangent vectors to the whole manifold, such that there exists a smooth curve to the manifold, such that at zero it equals to the given point, and its derivative at zero is the given tangent vector v. So this tangent cone.
You mean
Tangent P?
Oh, I'm sorry, you're right. Thank you. Is a convex polyhedral cone. Okay.
It's this first definition of a polyhedron. If the manifold were just Euclidean space,
Yeah.
How exactly is a regular polyhedron locally diffeomorphic to that? I mean, there are different P's and Q's, and there are vertices and edges. It's a little peculiar. I mean, P depends
first
on,
of all, any smooth submanifold in Euclidean space is a special case of.
but a polyhedron isn't.
It is polyhedron. Smooth submanifold is a polyhedron.
No, but I'm asking whether a polyhedron, an ordinary polyhedron, is a
Oh,
polyhedron.
it should be simplicial. If it is ordinary convex polytope,
Yeah.
is simplicial, namely all vertex has at most n edges, adjacent edges, then it is polyhedron. Otherwise, it is not, according to this definition.
Doesn't look like it's locally diffeomorphic.
Yeah, so the question is if you have two lines that are at an angle that isn't 90 degrees,
Lines, yes.
not 90 degrees, like 30 degrees. Yeah, so what is the diffeomorphism to the quadrant?
It is not differentiable polyhedron.
Okay, I
They're
think
not
that's
the-
your question.
Yeah, and you answered it. These are not polyhedron.
Yes,
Polyhedron
okay.
are not polytopes.
Right,
necessarily.
right.
Okay, thank
No,
you.
but it's simplicial, right? So it doesn't matter.
No, I don't.
What do you mean by
Okay, good.
it doesn't matter?
Angle is diffeomorphic to right angle.
If it is just broken line, it
No,
is not
because it's not differentiable at the origin. It's not,
Yeah.
right, the diffeomorphism won't be linear at the origin. Oh, it's
Angle
gonna
is
be
linear
also
map.
differentiable.
Yeah.
No,
Okay,
sorry.
I'm-
So,
I take it back. Yeah.
Oh,
So
okay.
what you said at the
So wait a
beginning
minute.
is correct,
Yeah,
I believe.
Okay.
Right? So if you have enough,
Right, so maybe we
not too
shouldn't
much
try to think about
vectors, so you
examples.
just bring them by linear transformation.
If you have a triangle on the plane, it is differentiable polyhedron.
It's a
But
bad
its
name.
boundary is not.
Yeah. Okay.
Boundary.
Okay, it's just okay. Okay, so this is a convex cone.
P and the Q can change depending on the point. Is
Yeah,
also-
yeah,
In
yes,
other words,
yeah.
locally, you have a different P and Q. In other words,
Oh yes, there is no restriction to P and Q
exactly.
except
They can
that
vary.
the sum is at most time.
All right, and that was what you were talking about with the symbol.
Both could be zero, like for a point.
Okay, thank you.
We define dual cone. So to be all cotangent vectors at the same point, which take non-positive values on the tangent cone. This is also convex polyhedral cone. And finally, we define a characteristic cycle of P to be union over all points of P of this dual cones. And this is a certain subset, is a cotangent bundle of the manifold. This characteristic cycle is a generalization of conormal bundle to smooth manifold. Indeed, it's easy to see that if P is closed submanifold, then its characteristic cycle is just convex, conormal bundle in the usual sense. But in general, characteristic cycle is a closed Lagrangian subset, submanifold with singularities, submanifold with singularities of dimension n. Dimension of characteristic cycle is always n, no matter what is the dimension of P. For example, characteristic cycle of a point is cotangent space to this point, which is n-dimensional. Now, central definition of smooth valuation. Definition: a functional phi on all differential. This is a family of all differentiable polyhedra. Scalar valued function is called a smooth valuation. If there exists a differential form of degree n on the cotangent bundle, such that, first of all, the restriction
Pm, the collection of all differential polyhedra.
This is collection of all differentiable polyhedra. The restriction
They
of
could be non-compact.
what?
They could be non-compact.
No, they are compact. I think. Oh yeah, they are compact. The restriction of canonical projection to the manifold to support omega is proper. And second, phi of any polyhedron P is equal to integral of omega over the characteristic cycle of P. Well, I will not comment on the motivation of this strange definition. My original axiomatics was different but equivalent to it. But for expository purposes, it's the shortest way to introduce smooth valuations. Let me have a few general remarks on this notion, and then I will give examples. First of all, we denote the space of valuations, of smooth valuations by V infinity of M, smooth valuations. And it is can be considered as a quotient of the space of these differential forms with the first condition, modulo closed subspace of all forms defining zero valuation. So omega is highly non-unique given the valuation phi. So it can be checked that, okay, so it gives some canonical topology on the space of valuations, quotient topology, and it is not hard to check that we get Fréchet topology here. The Fréchet space. Some metrizable linear topology. Okay, now let me give you a few examples.
So you mod out by the valuations that vanish on all the polyhedra. Is that what you're saying? On these coated-
There are forms which define zero valuation. And there are many of them. It's infinite dimensional space. So valuations is a quotient by this of this space by infinite dimensional
vanish for all
subspace.
these.
The first example is all smooth measures is smooth valuations. All smooth measures in the usual sense are belong to smooth valuations. I forgot to mention one more general remark. These expressions of this form, smooth valuations, are finitely additive measures in the following sense. If we have differentiable polyhedra and subdivided to finitely many differentiable polyhedra in a nice way, so that all intersections are nice, then we have additivity of this expression. This is a basic property of characteristic cycle. Okay, next example.
Could you explain how a smooth measure actually gives such an omega? I mean, because you want it to be proper over n, right? How does it do?
Yes. You just take on. So let us, for example, consider flat manifold. Then locally, on flat manifold, cotangent bundle is consider M equals to Euclidean space Rn. Then cotangent space is good. And we take form omega to be, and here we have coordinates u and here p. F of u x1 x n, and also we multiply it by a function which has compact support along the fibers. Some cutoff function chi of p. And this differential form will do the job.
So is a smooth measure then in a canonical way such a functional or not?
Smooth measure.
I mean, you describe construction which seems to involve choices, right?
Yes. You see, when you integrate this differential form over characteristic cycle, how
the question is, are you
okay, to draw a picture, let me even simplify. Here is R. Let's consider segment, which is differential polyhedra. Its differential cycle looks like this. This differential form, this is Q, sorry. There's no piece. So integral of this differential form over these parts vanish. But over this part, it is something non-trivial. So it behaves like integration of top degree differential form over M. In general, characteristic cycle has this part and these parts such that omega on them vanishes. This particular omega vanishes. Okay, and the next second example is Euler characteristic. Well, And in this approach, it is not obvious to construct such a form for the Euler characteristic, but luckily can be deduced easily from generalized Gauss-Bonnet theorem. It was done by Allendorfer and Villey in the early 1940s, I think. They fixed a Riemannian metric of the manifold, and from this Riemannian metric, they constructed such a form, essentially. They worked on different language. So, as you see, Euler characteristic can be obtained this way by some non-canonical choice of Riemannian metric. These two examples will be important in the rest of the talk, but the next example, well, I will not use it heavily in the rest of the talk, but it is important example in applications of the theory to integral geometry. It is called intrinsic volumes. Essentially, this construction is due to Hermann Weyl in 1939, who did it not for polyhedra but for closed manifolds. Later it was generalized to polyhedra. Okay, so let MG be a Riemannian manifold. So now here is a certain construction behind this definition of intrinsic volumes. And fix an isometric embedding. Delta of the manifold to Euclidean space of sufficiently high dimension. It can be done using Nash theorem about isometric embeddings. Also, this year, this theorem was not available yet. So Weyl used some weaker results about existence of local embeddings, which was sufficient for this purposes. But we can use now Nash theorem and consider polyhedron P and its image in the space, in the Euclidean space, and take its epsilon neighborhood. And consider Euclidean volume of this epsilon neighborhood. The first observation due to Weyl, which is simple observation, that for sufficiently small epsilon, is this volume is a polynomial of the form epsilon to power codimension, sum I from 0 to n, epsilon to power n minus I, vi of p, and there are certain standard normalizations, which I will not write down explicitly. Okay, so there are n plus 1 non-trivial coefficients, and this is called I's intrinsic volume. So, why it is called intrinsic? The non-trivial theorem proved by Weyl for closed manifolds, closed polyhedra, and generalized later to any differentiable polyhedra is that these coefficients, so theorem vi of p is independent of the isometric embedding Euler. And surprisingly, it is a non-trivial result. So these intrinsic volumes are smooth valuations. So what can be said? Some of them are certainly familiar to you. Vn, it is just Riemannian volume of the polyhedron. V0, it is in fact contents of Eindorfer-Weiss theorem, that it is Euler characteristic. But let me say another one. It is half of n minus 1 dimensional volume of the boundary. Okay, but there are more intrinsic volumes. Okay. The space of one of the most interesting structures on the space of valuations is multiplicative structure, which I'm going to discuss now. I will not define it precisely due to lack of time, but later I will interpret this product in some more familiar terms in a certain special situation. So I will discuss in some details multiplicative structure. So the following theorem first was proved by me on Rn and then jointly generalized to arbitrary manifolds with Joe Fu, says that on the space of smooth valuations there exists a canonical continuous product which makes space of smooth valuations a commutative, associative algebra with unit, which is Euler characteristic. Euler characteristic is the unit in this algebra. Furthermore, this product satisfies the version of Poincare duality. Consider the bilinear map on smooth valuations on M times smooth valuations on compact support to scalars. So compact support is defined as Euler. Given by phi psi goes to product phi psi in the sense of previous theorem, evaluated on the whole manifold M. Product by compactly supported valuation is compactly supported, and it can be evaluated over the whole manifold M, even if it is not compact. But for simplicity, at the moment, it is not very restrictive to assume that the manifold is compact. So, okay, consider this bilinear map. It is a perfect pairing. And which means for any non-zero valuation phi, there exists valuation compact support psi such that p times psi evaluated with the whole manifold is non-zero. And the other way around, for psi, the non-zero psi, there exists phi such that this expression doesn't work. In other words, the induced map from smooth valuations to the dual space of continuous compactly supported valuations is injective and has a dense image, big topology. This is equivalent to the fact that the parent was non-degenerate. And okay. So, for instance, on compact manifolds, it means that smooth valuations are embedded canonically into its own dual. And this dual space I will denote as a space of generalized valuations, which is somewhat very much, in fact, analogous to the space of generalized functions in analysis. Okay.
In some sense, part of it, you started with something which is already a valuation, which is the volume, right, Vn. You obtain out of it.
And what?
You obtain out of it other evaluations, which are v0 to Vn minus 1, by adding things up and expanding it.
I'm not sure.
I'm saying you're on the right-hand board.
Yes.
Right, you took the volume, which is a kind of evaluation.
Yes.
Then from it, by expanding this polynomial, you get other valuations on M.
Yes.
And I'm asking, is that something general? Is like if you plug in a valuation, can you get other valuations by consider the way that
it can be made general, but slightly different. It can be made general, but it requires a little bit of modifications and saying right words. But indeed, it's pretty general. The only thing which is not general is this theorem of while these coefficients do not depend on the embedding. This is something very exceptional. Okay.
Can I ask in the same? You said in the first theorem that it's canonical. What does it mean? Does it mean that there's some maps between M and N to manifolds and this is compatible? Or?
Canonical, I constructed a map from smooth valuations to dual space of compactly supported valuations, which does not, it is canonical in the sense that it doesn't involve any extra structures, choices.
For example, if there's a map between two manifolds, is there a map between the two valuations?
There is, in fact, two maps, pull back and push forward. They are defined partially. There are some non-trivial analytic questions to overcome. So morally, they exist, both pull back and push forward. But technically, they were defined only under restrictive assumptions of maps being immersions or submersions. Not for RB, but morally they not always, but more general situations.
Compatible with such maps. Product is compatible with such maps.
Pullback is a homomorphism of algebras. Never everything is defined. Push forward is not. Okay, let me give you examples of product. Simple examples, then I will give more. If we have new and new two smooth measures, as I mentioned, this is
Is push forward the module map? Is push forward the module map? Or something?
Over valuations on target space. But here the situation is similar, like in analysis. If you have generalized, okay, no, let me continue. So if you have two smooth measures, and we can consider them as valuations. If we multiply them as valuations, we don't get something interesting, we get zero. But Euler characteristic, as I said, is a unit in this algebra, and intrinsic volumes, their product is already non-trivial. Their product is another intrinsic volume with some coefficient which can be computed explicitly. Okay, now I would like to discuss more the meaning of product on valuations. And for this, it will be convenient to assume, things are more elegant, if the manifold is real analytic. Let us denote by introduce a space of constructible functions. Constructible functions on M. It is functions on this manifold, integer valued functions, such that locally level sets of F are subanalytic. Subanalytic set means that it can be defined by finitely many equalities and inequalities given by real analytic functions. This is a ring with obvious pointwise multiplication. And let me describe a map, a group map of constructible functions to generalized valuations. Then it will give us some extra intuition about various structures, in particular product of the space of valuations. Let us construct such a map. I remind it is just your space of compactly supported. So locally, any constructible function is finite linear combinations of indicator functions of closed subanalytic set. Indicator function of P, where P is Q, closed subanalytic. Locally, any constructible function is a linear combination of those, and we attach to it the following functional on compactly supported valuations. First, I will write a formula, and then I will explain what I wrote. So where omega is precisely one of the forms which define valuation phi. So phi of P is equal to omega characteristic cycle of P for any P differentiable polyhedron. But it is more tricky to say what is this characteristic cycle of subanalytic set. In fact, it was non-trivial to define it. It was done in the early 90s. This characteristic cycle of subanalytic set. Independently by Joe Fu using tools from geometric measure theory and Kashivara and Shapira using sheaf theory. Okay, so this map is uniquely characterized by its values on such indicator functions, and
Was omega unique was there a unique omega? I thought there were more than
one has to check that it is well defined. That for different choices of omega, we still get the same function. Now we extend. It will be convenient to consider extension to complex valued functions of the above map. And the claim is that first of all it is injective and it has dense image in the weak topology. So to summarize the picture we have so far, and which is often useful to understand general things of valuations. So we have large space of generalized valuations, which has two very different dense subspaces. Of smooth valuations and generalized one, and constructible functions. And it is often useful to understand various structures on smooth valuations by extending them first to generalized valuations, then restricting to constructible functions, which is much better understood space. Sometimes the other way around is also useful. And let me explain this in the case of product. So there is the following theorem, which is due to me and Berniak. It has two parts. I will not formulate them very precisely because very precise statement is very technical. So the first part says there exists a partially defined product on generalized valuations extending the product on smooth valuations. Partially defined, it means, let me make an analogy with classical analysis. Classical analysis, smooth functions is a dense subspace of generalized functions. And you cannot multiply arbitrary generalized functions. For example, to take square of delta function, one cannot do that because it badly diverges in any sense. But if the singularities of two such generalized functions are in some sense disjoint, or more precisely, they are wavefront sets disjoint, essentially, then we can multiply them. And two smooth functions, they always have empty wavefront sets, so we can multiply them as generalized functions and as usual smooth functions, and the result will be the same. Here the situation is very similar. Also there is some wavefront set condition. Okay, this is the first part. But now we have partial product here, and let us restrict it to constructible functions. And again, but one has to impose condition when product of two constructible functions as valuations is well defined. So let me make this assumption. So let PQ be two differentiable polyhedra in generic position. It means the singularities are disjoint in generic position. Then the product of these two constructible functions, product as valuations, product in generalized valuations, is equal to the usual product of constructible functions, which is just indicator function of the intersection. This is just pointwise product in constructible functions. Okay, so to summarize the product on valuations responds somehow to product on constructible functions, the usual one. Finally, I would like to describe a canonical filtration on space of valuations. It is a filtered algebra, and okay. Let me do it. For the purposes of exposition, I will start with constructible functions and then get here. Also, historically, the construction was different. So, define Wi, certain subspace of constructible functions. All functions dimension of support at least I. So it is decreasing filtration on constructible functions. Then I can take its closure of Wi in generalized valuations in weak topology. Yeah, I take closure. And then intersect just with smooth valuations to see what we get. Smooth valuations. And I denote this Wi. So we have W0, it is just the whole space of smooth valuations. W1, Wn. What can be said about this filtration? Let me summarize its properties. Wi are closed subspaces with respect to Fréchet topology. Second, Wn, the last term of this filtration, is just subspace of smooth measures. Something very familiar. It is compatible with the product, so we get filtered algebra structure. And the fourth property, the quotient of smooth value. Okay. W1, the first non-trivial subspace, is near radical of the algebra of valuations. And the quotient by this nil radical is canonically isomorphic to the algebra of smooth functions. In fact, this isomorphism is given by map valuation phi goes to function, just evaluation on points function. Point goes to phi of this point. So this map is onto smooth functions, it's homomorphism of algebras, and its kernel is W1. Okay. And actually, maybe I will mention one more remark, which
Have nice description for W1 mod W2.
there is a description, but I would need to introduce more background. There is such a description. Actually, well, this is to give such element in this quotient is to give at every point on the manifold on the tangent space valuation which is translation invariant and one homogeneous. Okay, and finally one more thing which I have time to mention. There exists non-trivial involutive automorphism non-trivial involutive automorphism of the algebra of valuations which preserves filtration, which extends by continuity to generalized valuations and being restricted to constructible functions. It is up to normalization, up to a sign is Verdier value or Euler-Verdier evolution. Perhaps in this context it's called Verdier evolution on constructible functions. Okay, I will stop.
Questions?
You say what the VIs are, besides V0 and for the constructible function.
I give certain description, but it is not probably very explicit. In terms of, for example, on the language of differential forms and cotangent bundle, there is a canonical filtration, point-wise. More generally, if you have some fiber bundle over some other base, on this space on differential forms on here, there is a canonical filtration. There is at every point there is a subspace of differential forms of degree 1, which vanishes on the fiber. And it generates certain filtered ideal. And WI can be obtained as valuations which can be obtained from differential form here.
I think I wasn't asking for the description of WIs, but the VIs. Intrinsic volumes. Yeah.
What is VIs?
Yeah, what are the VIs in the multiplication?
VIs.
One of them, Z0 is right.
This is constant which can be computed explicitly. It was computed, but
yeah, okay, but I still don't know quite what VI is as a in other words, what's it supported on? I mean,
what's V2? Oh, this is a question. Okay, let me give you more examples.
Yeah, sure.
So about VIs. Well, as I said, V0 is Euler characteristic, Vn is just Riemannian volume.
Yeah.
Vn minus 1, it is 1/2 volume n minus 1 of the boundary. Now, if we have closed polytop, closed, then Vn minus 2 of P up to some normalization, it is integral over P of scalar curvature of P. With respect to volume differential with respect to volume on P. If we have some hypersurface in Euclidean space, then this V's can be obtained as integral over the surface of some elementary symmetric polynomials and principal curvatures.
So just like there's a map from volumes to these valuations, is there one also from K forms to these valuations? Can you lift, if you have on the manifold, differential, for example, a function? It seems like you can define a valuation using the function on the manifold. Smooth function.
If we have smooth function, I'm not sure. So we have this canonical homomorphism of algebras onto smooth functions, right? But I don't think it splits.
No, but I'm not saying it's a canonical. But if you choose in each fiber smoothly, compactly supported n form, then you have a map the other way.
Yes. In each fiber, you fix form.
An n form.
Yes, you can.
For example, this gives you another subspace, a map from the subspace of functions into the space of valuations.
Yes. This is non-canonical, but you're right.
And the product you define would then correspond to product of functions.
I'm not sure. I never tried this, but if I had to bet, I wouldn't.